We've seen that some combination of deposition and diagenesis determines the petrophysical character of the reservoir rock. This means that with geologic data, we are usually able to predict only general conditions of fluid flow within the reservoir. For example, diagenesis may have created high permeability zones or permeability barriers in a particular facies. What the engineer needs in order to predict fluid flow behavior, then, is quantitative data on specific properties of the rock which determine fluid saturation and movement. Much of this data is derived from the analysis of core samples. Let's look for a moment at the more important measurements that are made. Certainly saturation, porosity, and permeability measurements are required. We might remember, though, that where porosity is almost independent of grain size, but very dependent on sorting, permeability is a function of both grain size and sorting. This makes it much more susceptible to rapid local change. To predict permeability distribution in areas where only log data exist, we must often make use of a porosity-permeability correlation plot, such as this. The correlation is usually valid over limited range, not linear, and is much better in sandstones where the original relationship between porosity and permeability is best preserved. It's also most applicable, of course, when used on a facies-by-facies basis. Standard permeability data from core analysis are usually reported with only one fluid present, usually air or helium, at 100% saturation. These values of absolute permeability certainly have their uses, but what the engineer really needs in order to estimate reservoir performance are relative permeability data, which, as you remember, describe the flow behavior of one fluid when there are two or more fluids present in the reservoir rock. In addition, capillary pressure measurements made on core samples are extremely valuable because they provide us with such crucial information as pore size distribution, the sealing capacity of permeability barriers, such as shale intervals and faults, the thickness and location of the oil-water or gas-water transition zone, initial fluid saturation, and residual oil saturation after both primary and secondary recovery. As we might expect, many of these petrophysical properties are interrelated because they depend on the detailed nature of the pore system in the reservoir. They therefore can be grouped according to facies, which of course brings us back to geology. Our next step then is to correlate these data against well logs, and thus integrate them into the geologic model as a whole. This is called rock typing. Each rock type will show a consistent and distinct set of reservoir properties. It is important to recognize that often a single facies, such as a point bar sand, will be subdivided into several rock types. This is useful from the engineering point of view, too, because reservoir performance will differ for each rock type.